Okay, so let's do problem number 23. Okay, so problem number 23 is basically 4 resistors. So here we have, so circuit problem number 23 is basically a battery. So here's the positive side, here's the negative side. And it's connected to a resistor, which has another resistor and another resistor. And then we have another resistor over here. And so, okay, so here is your voltage, happens to be given as voltage is, what does it say? 50 volts. So 50 volts. And what is R1? R1, R2, R3, and R4. So this is R1, this is R2, and this is R3 and R4. So R1 is equal to 10 ohms, 10. R2 is equal to 10, R3 is equal to 10, and R4 is equal to 15 ohms. Okay? And so, first step, notice that R1 and R2 is in parallel. So actually I didn't read the question. Let's make sure. Find the current through the batteries, question number 1. Find the voltage drops across each of the resistors, and what is the power loss in each of the 5 resistors? Is it 23? Oh, I think it should be 4 resistors. It's only 4 resistors, unless you're putting resistors for the battery. These batteries do have an internal resistance, but these numbers are so small. But anyway, so here's 50 volts and R1, R2, and R3. So find the total current. So we're going to replace this into one circuit. So these 2 resistors are going to be replaced by a single resistor. They're in parallel, so we have to use 1 over R12 for the replacement resistors of 1 and 2. Is going to be 1 over R1 plus 1 over R2. And so this is equal to 1 over 10 plus 1 over 10. So R12, so this is 2 tens, and so this is 5 ohms. You should plug into a calculator just to make sure. Yeah, so R12 is 5 ohms. So now we have a circuit. We replace this parallel series into one resistor. So now we have a battery that's pointing this way. So this is R1 top resistor, and then we have a replacement resistor of R12. And I'll write this over here. R12 is now, we've calculated to be 5 ohms. So let's leave it at that. And so V. So we replaced R1 and R12, R1 and R2 with R12. So now these are in series, so the total resistance is going to be, let's call it R1, 2, 3, and 4 for all 4 resistors, or 3 resistors in this case, R1, 2, 3, 4. It's going to be equal to R1 plus R2, 3 plus, oh, I'm sorry, I made a mistake. So this is actually R3, and this is R4. So R3 plus R23 plus R4. So R3 happens to have value of 10 ohms. R23 we calculated it to be 5 ohms, and R4 has we calculated that to be well, we looked it up, and R4 is 15 ohms. So we get 30 ohms as the final resistance. And so we've replaced this whole circuit with a simple circuit. So this is R1, 2, 3, and 4, and this is your voltage. And so we can calculate the current going through the circuit. And the current in the circuit, actually I'm sorry, I made a mistake. Remember, conventional current is always plus to minus, so it's going down. So make tons of mistakes, and that's okay. Everybody makes mistakes. The point is that your understanding of a concept is what's important, not superficial things like calculating numbers. That's superficial. It's meaningless when you have real complicated problems. So your understanding of the concept has to be reinforced, not these calculations, not that. So anyway, V is equal to I. Current is going down, going across R1, 2, 3, 4. So what is the current I? It is the voltage V over the total resistance. In this case is R1, 2, 3, 4. And the voltage happens to be 50 volts. The resistance 1, 2, 3, 4. R1, 2, 3, 4 is... where is R1, 2, 3, 4? Oh, here we go. I should write this down over here. R1, 2, 3, 4 is 30 ohms. 30 ohms, so we're getting 1.6, so I'll round it off to 1.7 amps. So I'm only doing two significant digits, so this is really 1.7 amps. So remember, this is written as 1.7A, capital A, but I'm not trying to use any units because they'll get confused with variables. Once you get confused. So the current going through the circuit is, from the battery, is 1.7 amps. This is actually 1.67 amps, but I'm rounding it off to two significant digits only. Okay, so it's 1.7 amps. Okay, and I put a number in there. I didn't want you to be confused there, so let's erase that. Okay, so what is so find the current through the battery, find the voltage drop across each of the 4 resistors. Okay, so let me erase everything. Okay, so I think I have everything I need. So I'm going to erase everything over here. And so this is now we have to do a little, make sure your understanding of batteries. So whenever you have a battery and it's labeled as 50 volts, what you're saying is that the bottom plate is 50 volts higher than the negative plate. And when it's on the minus side, you're actually saying it's 50 volts less than the positive side. So it's actually relative volts. Make sure you understand that the batteries, right, are not plus 50 and minus 50, or plus 50 and minus 50, so there's a potential difference of 100 volts. That's not true. So just make sure you're not making a mistake on that. So instead, we're actually saying that this side is 50 volts bigger than the other side, and this side is negative 50 volts than the other side. That's a plus and minus. Okay, so we need a reference voltage, and if you kind of remember, I'm going to actually say there is, so we want to convert a relative voltage into an absolute voltage so that we can actually do some calculations. So I'm going to say on this side, right, the potential is going to be 0, and I can do this with basically a grounding symbol. And so this means that the potential at this point, V, let's call this, let's actually label these. So this is VA, and this is VB, and this is VC, and this is VD. And remember Kirchhoff's law, right? The sum of the differences is always 0, so we can actually do Kirchhoff's laws. But so VD, I'm going to select this to be 0. So what is VA? It's 50 volts bigger than VA, so 50 volts than VD, so VA is equal to 50 volts. So the next question is, how do I calculate VB? So to calculate VB, I know that there's a voltage drop going from VA to VB. It drops in voltage. Okay, so if you kind of remember Kirchhoff's laws, right? When we did Kirchhoff's laws, which is coming up in the video soon, we know that we did the plus side, so the potential here to here must be smaller because the current is going through here, so this must be at higher potential at this point. And this point must be at a higher potential at this point because that's why there's current flowing that direction, and this point is higher than this point. So we can label it a plus and minus. Okay, so VB is actually going to be lower than VA, but by how much? So we can actually calculate the voltage across A and B. I'll label it as AB is equal to the current flowing through that circuit, right? Which is, which is equal to I times the current flowing through here is I times the resistance of R4. In this case, it happens to be 1.7 times R4. R4 happens to be, where's R4? 15. And this is 15 times 7, or you can say it's really 1.6, 2.55, but I want you to use a calculator, okay? don't do what I'm doing. I really want you to use a calculator because there's nothing smart about getting these calculations, nothing special about these calculations. Okay, so this is should be 25.5, but let's say, so I'm plugging it in just to make sure that hopefully I'm teaching a lesson about using a calculator. So I get 25.5, which I'm going to round it off to 26. So there's a potential, and I'm putting variables again, sorry. So difference between A and B is 26 volts. So what you're saying, right, is that the voltage drop going from VB is 50 volts. The drop from here to here is 26 volts. And so my absolute relative to this VD, right, so this is actually 50 minus 26 volts here. So the voltage drop is 26 volts, which is 26 volts, which I'm willing to write out. But VB, right, is 50 volts and less by 26 volts. So plug into your calculator, right, and hopefully you are getting this as 24 volts. So this is the voltage at this point, volts. And remember, I'm only doing this 2 significant digits, so we'll get the last digit will have some errors in it, but that's fine as long as the procedure is correct. And how do I calculate the potential at VC? Well, I can find the currents going through here. I can actually split, well, we can replace this by our resistance, right, VC. So we have R12 together is replaced by one resistor, and so we can do it that way. Okay, so let's do it that way. Okay, so I'm going to replace R1, R2 by one resistor, which is R125, and so VC, the voltage drop from here to here is that one resistor. So the voltage drop, which is, let's call this BC. BC is going to be the current going through the circuit, this one resistor, which in this case is 1.7 amps. So this is the current I times R. So this is 1.7 amps times the resistance of, where is it? R12 is, where is it? 5. Okay, so this is really, so I'm going to use the calculator, but even though you should be just saying it's 170 divided by 2, but 17 divided by 2, and we get 8.5 volts. I'm only doing 2 significant digits, so let's leave it at that. Okay, so 8.5 volts dropped across from here, VA to VC. Actually, I should write these numbers down. And we can repeat the procedure again from what's the voltage drop across VC to VD. And that's equal to the current going through that resistor I times the resistance of R. So this is R12, right? R12, and this is R3. So this is 1.7 times R3 has a value of 10. So this is 17 volts. And you might say, look, 26, so remember, 26 plus 8.5 plus 17 is 52 volts. But remember, the last significant digits are off because we're only going to 2 significant digits. So the sum of the voltage drops is equal to the applied voltage of the battery. And I think that was the question, right? Find the voltage drops across each of the resistors. What is the power loss in each of the 5 the resistors? Okay, so a little more calculation to do. So let's calculate the power loss across R4. Let's call it P4, and that's the voltage across resistor. So this is R4, the voltage across, which is AB, I guess, times the current I. In this case, it happens to be 26 volts times a current value of 1.7. So I get 26 times 1.7 equals 44 watts. Okay, so it's actually just 44W, but I don't want to use single letters, so just make sure you understand. So this is the power loss across R4. So we can actually do a power loss individually, or we can do it collectively. So if I want to calculate the power loss from here to let's do R3 instead. So what's the power loss across 3? It's the voltage drop across VCVD times the current going through that circuit. So voltage is the voltage across CD, which is calculated as 17 volts. And the current is 1.7. So 17 times 1.7, which is 17 squared, which is 29 watts. Okay, it's 289, but so make sure you're using the calculator, because I don't really care if you can do things in your head. Nobody says you're a great mathematician because you can multiply a whole bunch of numbers together. Okay, so here is it's now what's the power loss across this resistor, and we can do it a couple of ways. So I'm calculating the power loss across each one. So let's find the current going through R1 first. So let's calculate the power across R1. So what is the current going through I1? I1 is equal to the voltage from VA to VB, which we calculated as VBC, which is 8.5 volts. And so it's 8.5 volts divisible by the resistance R1. What is the resistance of R1? R1 happens to be 10, so this is 0.85 amps. I'm only going to do 2 significant digits, okay, so it should be really 0.9, but let's not go to it. So I2 is going to be the same thing. I2 is going to be 8.5 volts drop from here to here, divisible by 10 ohm resistor from here to here. So again, we get 0.85 amps. Can you see this? Yeah, it's on the board. And so what's the power across that resistor? Enough space. I'll start erasing something. I'll just do it over here. So P1 is going to be the current in I1 times the voltage across 1, which happens to be VBC, right? So in this case, it happens to be 0.85 amps times a voltage drop of BC. BC happens to be 8.5. And I'm just going to... VBC is 8.5 volts? Yeah. 0.85 times 8.5 gives me 7.2. So 7.2 watts. And it's the same number for P2 also, because it's the same current, amount of current. I2 times VBC, which is 0.85 times 8.5 volts, and that's 7.2 watts. Okay, so we did a lot of calculations, and you'll actually find that the total energy loss across the resistors must be equal to the total power generated by the battery. And we can double check, so it should be 7.2 watts plus 7.2 watts plus 44 watts and 29 watts. Let's double check, make sure this is correct. So CHK check. So 7.2 watts plus 7.2 watts plus the resistor R3 is 29 watts plus 44 watts, and I have 87 watts. So 87 watts of energy is being lost in this resistors. So what's the battery? Battery says that we have a voltage of 50 50 times, and the current is 1.7, and we get 85 watts from the battery. And within our calculation position, we can see that they're about the same. So it's just our precision is off because we're only doing to 2 significant digits. Okay, so 85 watts are being generated, and approximately 85 watts, which is 87 watts, are being lost at the in the resistance, in the resistors, or 87 watts in our calculations, right? And that's expected because of precision calculations.